I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy, Haleakala Division. And it's my pleasure to put these talks together for the community, and we're getting a bigger web community each week, which is, I'll say hello to all the web community people here too. This week we have Cooper Downs. Cooper is a graduate student over at the University of Hawaii Institute for Astronomy in Manoa, working with Dr. Ilya Rusev. And, you know, when I was talking to him about his introduction, he said that he didn't have any good, secretive stories. But I talked to some of his friends from undergraduate. No, but very seriously, he's a great guy. He's doing some very interesting modeling of the sun and the upper atmosphere. And so let's give him a nice, warm Maui welcome.
Great. Well, thanks for that introduction, JD. I appreciate it. And thanks to everyone here for coming out. Really nice turnout, and I appreciate you showing up. Yeah, so again, my name is Cooper Downs, and I'm a graduate student at the University of Hawaii. We're mostly housed in Manoa, and that's where I reside on Oahu. And just a list of my collaborators, there's Dr. Ilya Rusev, my thesis advisor. Noi Wugaz, he's a researcher at IFA Manoa. And then also I work a lot with the University of Michigan and their space weather modeling team with these guys here. And a bunch of logos, just there's a lot of institutions and things that go into this. And again, about me, I've been a graduate student since fall 2006. That's when I started, and right now I'm in the final year of my dissertation project. Originally, before Hawaii, I'm from the San Francisco Bay Area, and I did my undergraduate studies at University of Santa Cruz. And just because I didn't have any other anecdotes for JD, just a little one is when I first came to college, I did undergraduate. I thought I was going to be a music major, but I wasn't really decided on what to do. And one of my electives in my first quarter there was a gravitation. It was an astronomy elective for undergrads. And ever since like the first lecture of that class, I was just hooked. It was really interesting, and the guy there just expected a lot out of his students and tried to teach us a lot about the universe. And I think that's one of the great things about astronomy. There's just so much interesting stuff out there. So. And my current thesis project is nothing to do with gravity, really, but it's adapting a computer model to study the solar atmosphere in the case of large-scale waves, and I'll go on to explain what all that stuff means. So in this talk, I'll give you guys a background, and I emphasize brief because there's so much solar research being done, especially right here at the IFA Maui, but this will all sort of be in the context of what I do. I'll try to give you a brief description of computer models and motivate why they're one tool that's very useful for researchers to learn more about the sun. And then I'll present my research application, which has to do with EUV waves, and my modeling effort, and also some of the results that are going into my dissertation. All right, so what I really like to introduce when talking about the sun is that the sun is a star. And in classical astronomy, there's all sorts of studies for stars. And what makes the sun so different is that its proximity. And so traditionally in astronomy, you think of stars as point sources. Up until recently, at least, that's been the case, where you treat them with one-dimensional models. And what's rich about stellar astronomy is the very many different types of stars out there. And actually, the sun is sort of a boring type. But what's neat about the sun is how close it is to us. And that really changes how we can study the sun. And so here's a picture of the sun. Here's a very tiny sunspot. But the sun is actually, because it's so close, we can resolve a lot of interesting things going on. And so here's this, just to give you a sense of scale. This is the sun here, but then this little dot is actually slightly bigger than the Earth. So this is a very large object, but something that we can see in very high detail. And so here, let me move my mouse. This is a movie of a sunspot evolving during the course of a solar flare. And you can see on very, very small scales, there's a lot of dynamics going on. And in the center here is a big magnetic field, and there's some surface evolution on there. So this really gives us a unique perspective of this astrophysical object, our proximity. And another thing that makes the sun so interesting, it's not only a star, but it's a magnetic star. And magnetic fields are universal in astrophysics, but the solar magnetic field is really quite interesting. So here's a sort of what some might call a boring version of the sun. That's a nice round ball. But now let's take this same day and put the moon in front. And here's a solar eclipse image. And so what we see here is that it's really not just a boring round ball at all, but it's the magnetic field that completely changes the structure of the sun and is really quite complicated. So the first point is that the magnetic field leads to extreme inhomogeneity in the solar atmosphere. So no longer is it just a sphere, but we have magnetic fields extending outward, we have magnetic fields closing back over each other. And this really adds to the complexity of the atmosphere. And also the magnetic field changes in the sun. So there's what's called the solar cycle, which is a magnetic cycle that is the evolution of the magnetic field. And every 11 years, the solar magnetic field flips and really changes the way in which we observe the sun and sort of the face that it presents to us. And this atmosphere here is what we refer to as the solar corona. It's the outermost atmosphere of the sun. Unlike the photosphere, the solar corona is very, very hot. So instead of a few thousand degrees, it's a few million degrees. Additionally, the solar corona is very sparse, very low density. So the density of the solar corona in these units is 10 to the 8 particles per cubic centimeter. To give you perspective, air is 5 times 10 to the 20 particles per cubic centimeter. So essentially, the solar corona is 1 trillion times less dense than the air that we experience on Earth. So it's not only is it 1 million degrees, it's just a very, very exotic environment compared to what we experience day to day here. And this part of the atmosphere, these are various images of the corona. This is as seen on the disk. This is just outside. And then the extension of the solar corona. As I said before, the solar corona is coupled very strongly to the solar magnetic field. And also the solar corona extends out into space all the way to Earth, all the way past Earth, past the planets. And that's what's called the solar wind and sort of interplanetary space, or the heliosphere. And one very common way that we observe the sun and other astrophysical objects is through photons, electromagnetic light, visible light. And this is a way that we can observe things that are very far from us. And it is really the richness of the electromagnetic spectrum, so we're talking about radio waves, visible light, X-rays, that can provide us a wealth of information about these objects. And each wavelength or color of light gives a unique piece of the puzzle, and this is particularly true for the sun. So again here, this is the sun as one might see it in the visible. This is showing the photosphere, and you say, well, okay, there's a sunspot here, but relatively sort of quiet. But then by analyzing a spectral line in the visible light, we can actually determine the magnetic field. So although we might not be able to see it directly in broadband visible light, there's a tremendous amount of information contained in visible light. And this right here is the surface magnetic field. And then if we look at the ultraviolet, we observe a different part of the solar atmosphere. And this is the chromosphere, which I'm showing here. This is slightly hotter, less dense, and extends outward beyond the photosphere. And you can see it reflects a lot more of the magnetic activity that was harder to see in visible light on the sun. Going further out, going smaller in wavelength, we go to the extreme ultraviolet. This is one spectral line that is continuously taken by satellites in space. And again, the magnetic complexity just continues to grow as we move further outward from the sun and higher up in temperature. And then this is full-on corona, temperatures of 1 million degrees, what seem to be just a few spots here and a few spots here is actually producing a tremendous amount of structure out in the sun. And by the way, before I continue further, I do like, if people want to ask questions or anything like that, just raise your hand or let me know. It's fine with me. So this is a broad view of the sun, but current instruments are able to look at very fine details of the sun and the solar corona. And so this is zooming in on this region. There's a tremendous amount of structure and scales that we can observe. And here are coronal loops, essentially density enhancements that extend from sunspots. And here is a video from the same instrument showing sort of the quiescent evolution of the corona. And there's things going on from large-scale changes here in the center of what's called an active region, but also the entire area around is changing in subtle ways. So the sun is a very, or the outer atmosphere of the sun, the corona, is a very rich and dynamic environment, one that's constantly changing because of the magnetic field. And again, I guess some of this is repetition, but all of these different views of the sun are tied to looking at different parts of the electromagnetic spectrum, so different colors of light. And as I said before, what the main part of emission changes as you change your temperature of the atmosphere. So the photosphere is 6,000 degrees. It emits in the visible light mainly. But the corona is 1,000,000 degrees, and it emits electromagnetic radiation in extreme ultraviolets, very short wavelengths. And all of this is intimately tied to the thermodynamic state and the composition of the sun. So from these observations alone, we can learn a large amount of information about the sun. And in addition to sort of the quiescent evolution of the magnetic field of the sun, there's also some very dynamic evolution that we observe. So ever since the launch of the SOHO satellite in 1996, we've been continuously observing what's called coronal mass ejections. By looking at scattered light in the corona, we can watch it change, and these are ubiquitous events. They're related to rapid changes in the magnetic field releasing energy, and they shoot material and particles out into space as they happen. And these are various pictures. So this is maybe about the size of the sun here, and then they can extend very far out in the sun and reach us here on Earth. Now, coronal mass ejections are very important because they disrupt the ambient conditions of the space around the Earth and in the solar system. Coronal mass ejections, due to their intensity, can accelerate charged particles, and these charged particles can interact with spacecraft and things on Earth. They interact directly with Earth's magnetic field. Coronal mass ejections are what cause aurora and things like that. And they're intimately tied to the evolution of the magnetic field. And this is something we as researchers really want to understand. And just to give you another visual concepts of what this looks like, I got this from the NASA website. So this is a coronal mass ejection close to the sun. This circle is the solar radius. And these will propagate all the way to Earth. Here's an artist rendering of Earth's magnetic field. And so this gives you an idea that the magnetic changes on the surface of the sun can drive and interact with Earth's magnetic field very far away. And here's a video from the same website that gives you sort of an artist animation of what that might look like. So we have a very large CME from the sun. It travels all the way to Earth, and then all this stuff going on here, this pulling back of these various surfaces, represents how it's stretching and pulling Earth's magnetic field and interacting with it. So as this is going on, particles trapped in this coronal mass ejection will be able to stream down to Earth and cause aurora and are measured by satellites and things like that. And maybe we'll repeat one more time. Yeah, here we go. So just, this is to give you an idea of what space weather looks like and sort of motivate why people are interested in studying these sort of things. Because it has very tangible connections to our atmosphere here on Earth. And especially now that we have a lot of satellites in space, these little things right here, those are all the orbits of different satellites. And if you're outside of Earth's magnetosphere, the electromagnetic changes due to a coronal mass ejection can be very strong. So we want to understand this sort of thing, and just naturally, from a scientific perspective, you want to find some physical way to describe this system. So what's going on? We observe this with satellites. People have been observing the sun ever since Galileo's time, or even before with the naked eye. And in order to do this, we can combine our understanding of physics here on Earth, our ability to observe the sun, combine these two, and then you get astrophysics. That's the way I like to think about it. And with this system, it may sound facetious, but you always want to start with the simplest understanding of the system you're looking at. And we know that the sun is a plasma, and so we turn to what's called magnetohydrodynamics, which is a fluid description of a plasma. It's essentially, ever since the 1800s, or really the mid-1950s was when MHD really became its own and was standardized. We take our most basic understanding of physics and can describe plasmas. And not that I'm expecting anyone to read these equations, it's just a visual example. MHD represents sort of the basic physical tenets that you learn. This equation represents mass conservation. Mass is neither created nor destroyed. We use force balance, effectively Newton's laws, that gives us momentum conservation. Conservation of energy, another fundamental tenet in physics. We can write the simplest energy conservation equation to describe a plasma. And we can close this whole system by writing an evolution for the magnetic field. And so this is all good. We can come up with an equation, but what about real life? And this is a problem because these equations, while very elegant, become very difficult to solve on paper for even the simplest of systems. And as I showed you before in those pictures, the sun is actually quite complex in terms of geometry and time evolution and density scales. So one approach for understanding a system like the sun is to study idealized systems in geometries. So take what we see and make a 1D model, or use symmetries to do a 2D model. And a huge amount of intuition can be gained this way. I'm not trying to diminish this in any way. But for something that is inherently three-dimensional and dynamic like the sun, one solution is to use computer models. So I like to phrase the question sort of pictorially. So how can we self-consistently model this system? So we have some equations, but clearly there's some sort of disconnect between these equations and what we observe every day on the sun. And so the solution is turning to computers. So unlike here on Earth, when we do some laboratory experiments, we can't actually go to the sun and measure the properties everywhere in space. But with some sort of model, with a computer model, you can actually do this. One nice thing about computers is that they can solve millions of equations a second. So instead of having to have an army of people with a pen and paper, you can have a computer do millions of calculations. But of course, the ultimate caveat with using computer models is that you can put anything you like in a computer, but you need a human to tell you, well, does this actually mean anything or not? You can calculate a lot of grossly inaccurate things with a computer. So a visual example of what computer modeling looks like for the solar atmosphere. This picture here is showing magnetic field lines on the solar surface. And what you do if you want to, say, model the environment around the sun is you pick a volume. So let's put a big cube around the solar corona. We take this cube and divide it into millions of subcubes. So sort of something like this. And each one of these squares here represents a subdivision of this volume. And for each one of these subdivisions, these cells, you can assign it a value of temperature, density, velocity, and magnetic field. So the basic parameters that will describe a plasma. And then for each one of these cells, we can fill it with whatever we like, and then use our equations at the interface of each one of these cells to evolve our system in time. So you go a step, update every single cell, and then rinse, repeat. And this is analogous to weather models or fluid dynamic models or other things that have relevance to engineering problems here on Earth. And a nice thing about this sort of computer model, analogous to what people do for atmospheric models, is we can incorporate observations to study realistic systems on the sun. So like I showed you before and shown here, it's very easy to measure the magnetic field at the surface of the sun. And we can incorporate this at the boundary of our model. Use an extrapolation method to extract the magnetic field out into three-dimensional space. And then use that as input for our computer model to hopefully simulate something realistic on the sun. So that's the idea that by using a computer you can develop a laboratory to simulate something, some conditions on the sun that we can't solve with a pen and paper. And this is just to give you another flavor of what this looks like. This is a simulation done by my advisor. And with this sort of model, you can take theories of how a coronal mass ejection is initiated or evolves and plug it straight in and actually test and understand it. And so these models are useful for studying the 3D nature of the solar magnetic field. They're very useful for studying the initiation of coronal mass ejections and also their propagation and their relevance to Earth. And here's just another example. There are some very idealized models for how a coronal mass ejection might progress. And there are numerous types. So with this sort of model, you can put them in and change them and see what you get. So it's sort of like an experimentation to test various theories that people can come up with. And just to put this in perspective, there are many systems in what we call space weather. There's those that deal with the sun, but also those that deal with Earth's magnetic field, Earth's upper atmosphere, and also those that deal with the interaction of the solar wind with the edge of the solar system. And so there are computer models for all sorts of these things. And what I use is just a small subset to study the solar corona. And this SWMF thing here, that refers to the suite of modeling tools being developed at the University of Michigan. Yeah, absolutely.
Sodak asked if the solver type was an FETD or an FDTD.
It's a finite. It's not a finite element, so it's finite volume PDE solver, and you use that for hyperbolic problems. So it's one of the elements of fluid dynamics. It's probably the older one, and it's easier for MHD. It sounds like he's an expert. So, yeah. Okay.
That was a question from there.
Okay.
He says okay.
Great. So I realize that might have seemed sort of complicated, but the whole idea is that with these computer models, we can apply them to things that we observe on the sun. And so in my case, that application is EUV waves. And here's a movie of an EUV wave observed by the stereo spacecraft, which are two different spacecrafts at different angles that they view the sun at. And so what we see here, there's an active region here observed on the limb, and that's the same active region here. And as this coronal mass ejection progresses, we see material being ejected out this way. But at the same time, there's a very significant signal propagating across the corona this way. And that's what's called an EUV wave. And you can sort of see it propagate across the solar disk this way. And so these are very... and so this is a visual example of an EUV wave. And here's another one. And these are thought to be blast waves related to a flare or CME event, a coronal mass ejection. So you release a ton of energy all at once in the corona. And just like what happens during an earthquake, the analogy is that you release this energy, perturb the ambient environment very strong, and it launches a sound wave. The propagation, again, is in the lower corona. That's why they're called EUV waves, because that's the regime that we observe the low corona in. And they can affect a very large area of the solar surface. So shown here is just a difference of a half an hour. And remember, the sun is very, very large. So over a half an hour, we go from sort of a point source to much of the solar disk. So these travel at hundreds of kilometers per second.
And
sure.
so what is the effect that it has?
Well, some people think it might accelerate particles, but that's sort of debated. I think the most interesting thing is we're very interested in learning about coronal mass ejections, and this is one aspect of them. You don't get an EUV wave without having a coronal mass ejection, essentially. And so the properties of this wave can tell us about coronal mass ejections themselves, but also about the environment that they're propagating in. So I do talk about this later, but for example, if it truly is a wave, it should travel at the sound speed of the corona, of the material in the corona, and things like that. So it's sort of a diagnostic tool, and it's something we don't fully understand. So that alone, right there, means people want to, figure it out.
I'm kind of trying to imagine it from, if I were the sun, what would I be experiencing if this was happening to me?
Well, yeah, so it's easy. So if you lived on the photosphere, you'd actually be quite safe. These are very strong waves in the corona, but lower parts of the atmosphere don't feel this very much because they're much higher density and a much lower temperature, and the sound speeds are slower in those parts of the corona. So it affects sort of, and you'll see in later pictures, it affects a large part of the corona, but not so much down further below. And because the corona is so much less dense than the surface of the sun, it's just two completely different regimes, essentially.
Thanks.
Yeah, sure.
You were looking at the surfaces.
So here, it looks like the surface of the sun, but this is a picture of the corona. And then, but because we're looking in the ultraviolet, we don't see the photosphere, but we see the structure of the corona. So this is material at 100 or at 1,000,000 degrees, things like that. And then here's another view of this wave. So depending on what wavelength we look at, each of these false color images represents a different wavelength. This bottom one is about 1,000,000 degrees. The middle one is about 1.5 million, and this top one is 2,000,000 degrees. We see different features, and so that's telling us that this wave or this perturbation has a thermodynamic component to it. So if you follow where this arrow is, it's dark at the cooler temperatures, but then bright at the hotter temperatures. And so that's one interesting aspect of EUV waves. And then this is another example. Recently, NASA launched a satellite that has a very advanced observing capabilities, and so we can look at EUV waves at high resolution and high time cadence and see a lot of details. And so here's a movie of that. And so this is a lower temperature, medium temperature, and then a hotter temperature. And and this is over the course of about 40 minutes, at least at the start, where you can see this front go way out across the solar disk. And so this is about 400 kilometers per second that this front is traveling at. And also, another property of EUV waves is that they're inherently three-dimensional. So what's really nice about the satellites available to us now is that we can have three different aspects, three different viewing angles on the sun. And so this is the same event observed by Stereo B, the NASA SDO satellite, and then the Stereo A spacecraft. And depending on what angle you see this EUV wave at, it looks very, very different. And so that's another property of EUV waves, that they're inherently three-dimensional and extend out into space. And when we're looking at two-dimensional images and observations, it can become very difficult to interpret this because of the three-dimensional structure. So we need some way to understand that. And this is just a slide. Even though there are a lot of observations available about EUV waves, there's still no real firm consensus about their nature. So the main leading theory that I think has the most truth to it is the fast mode MHD wave, and this is essentially a sound wave in a magnetic medium, in a plasma. And people doing observations say, well, it's clearly an MHD wave. People doing models say, well, absolutely, it has to be an MHD wave. But then there's another group of people who say, no, this this isn't a wave at all. There are other properties that we can explain with the wave mechanism, and this has to be something else. Something called magnetic reconnection happens after this coronal mass ejection, and that's what causes the EUV wave. And there are people who do theoretical models for this, and also people who use observations. So the same set of observations can lead to a completely different conclusion depending on what author you look at. And there are also people like myself who try to include multiple aspects of these explanations. And just to give another picture of what a fast magnetosonic wave is, it is analogous to a sound wave. So the wave that is carrying my voice to your ears right now is the same type of wave that a fast mode magnetosonic wave would be. A magnetoacoustic wave is what they're also called. And the speed of these waves is governed by the plasma itself. So the strength of the magnetic field will dictate the speed, the density of the plasma, and also the temperature. And these are all things that we can measure or extrapolate when we're looking at the sun, or try to. It's the only form of magnetic wave that can really produce these sort of effects. It can travel across magnetic field lines. But unfortunately, one caveat is that the fast mode speed in the solar corona is not very well constrained. And so that can provide problems for different sets of EUV wave observations. And then this is just a picture of what a reconnection front might look like. You have your ejection here in the middle, and then it's perturbing field lines, and then as those perturbed field lines progress outwards, they'll reconnect with underlying field in the corona. So this is one way to have thermodynamic energy be released during reconnection processes that gives the properties of an EUV wave. But there are also other caveats associated with this theory. The first one being that it's very difficult to get reconnection to happen in such a controlled manner in the corona. And then also, in this case, you need heat transfer to be governing your signal. So that's one of the things. And I think what it all boils down to, why people cannot agree, is that it's very difficult to take these observations at their face value. So as you can see, this picture of the corona here, there's a lot going on. There are structures that are inherently 3D, protruding from the surface of the sun, and there are parts that are have very low densities and parts that have very high densities. And the way emission in the corona works is a lot like looking through fog. So you see through every single part. If there's more fog, you get more emission, but it's very difficult to tell exactly where in space it is if you only have one view. And then also, the emission properties of EUV emission depends highly on temperature and density, and so that adds another complication in there. And also, as I mentioned before, why computer models are helpful is that the equations that we use to describe plasma are very difficult to solve analytically for a system such as this. So all this leads up to the motivation for my thesis project here at the IFA. And so this project has essentially two main parts. It's ambiguously titled Exploring Dynamic Events in the Solar Corona, which means I can essentially choose to do anything as we continue. But the two main parts are first a model development phase. So one of the problems with existing models that we had when I first started this project is that we couldn't quite get all the relevant physics into the model that described the corona. And so there's some ambiguity or questions as to the accuracy of these models. And so we want to make a realistic model that we can use to study this phenomenon. And then the other aspect of this thesis project is to take this model and actually apply it to EUV waves. So what I really like to think of computer simulation tools is essentially my version of a laboratory. I'm not coming up with theories necessarily, but I'm taking these theories, developing a computer model, and applying them in a controlled setting. And ideally, we can simulate realistic conditions and dynamics and compare directly to observations. And this is critical because this allows for an interpretation of what it is we see from satellites. So that's important. And then another picture of a computer. This sort of thesis project takes a lot of computational resources. The software I use runs on supercomputers. So instead of having a single processor crunch numbers, you link 48 or hundreds or even thousands of times all together to make this calculation efficient. And relevant to here at the IFA Maui, just a few doors down, is this thing, which I like to call the thesis machine. But this is a supercomputing cluster which features 42 different computers that I run on. And it's got a really cool name. It's named after the Greek, or not the Greek, the Viking giant. So I don't know. It's fun. But then also another aspect of this project is sometimes you need more than what we have locally available here. And as I'm sure many of you are aware of, the Maui High Performance Computing Center has extensive facilities for this, and they partner with University of Hawaii. So some of the biggest simulations I want to run can run over just across the way at the MHPCC. And so this first part of the project, sort of summarized real quick, is, well, we want to develop a laboratory to study EUV waves. And so to go with the analogy, we have to start with some sort of equipment, some sort of basis for development. And that was what's called the Space Weather Modeling Framework, this University of Michigan code that's been developed by collaborators I work with at University of Michigan. But then we want to add something new. And for this, we want to study the low corona and ultraviolet emissions. So we have to add things like new physical terms, electron heat conduction, the radiative energy loss from this part of the corona, and also some sort of prescription for how the corona gets so hot. So these are new things we add. And then the rest of it is just sort of tweaking and developing the analysis tools that will let us get the experimental results for this thing. So mathematically, it's very important to have proper boundary conditions to describe your system. You want to have the right subdivision into cells of your system and things like that. And then also, one of the most key aspects of this is develop the ability to directly simulate observations, synthesize observations, so that we can compare and validate our model in this manner. And so that's a lot of stuff, but there's no real cool pictures for all this sort of development stuff. So I just sort of describe it this way. Well, the timeline for doing this is, well, first reading, figuring out what you want to do. Then programming, testing your programming, more programming, then realizing that everything you did in the past 3 months was wrong because it doesn't work, more programming, and then sort of rinse and repeat this process till you arrive at a stage where you feel like, actually, this is good enough to describe the system I'm interested in. So for me, this took half the time of my thesis, essentially. So 18 months later, we had a model in hand that we could do a first application. And of course, what you want to do with this sort of thing first is validate it and make sure that it actually can describe the system you're interested in. And I won't go over that. So to take that first work into a slide, this top row here, this is synthetic images from the model that I started with. So I included the ability to generate observations. And what this model didn't have was all the additional thermodynamics that are important for the low corona. And down here are observations. But then in this middle section, this is with probably one of the best runs to describe this these conditions for this set of observations. And what we did is include all these terms, all these new considerations, to ideally do a better job of simulating what the actual thermodynamic and magnetic conditions are in the corona itself. And so some of the results of this work were, well, we didn't just do one run, we did a bunch of different runs. And then this is just sort of them listed here. Because it's sort of like a laboratory, you can fiddle with some parameters, turn some things on in a controlled manner to sort of figure out what your system, what's going on. And one of the things is you can vary your boundary conditions, and hopefully your boundary conditions shouldn't make a difference in what you simulate. And we used two different things that were thought to describe this part of the corona very well, and they came out to agree quite well. And so that's exciting. You're not governed by some sort of mathematical problem at your boundaries. That's one of the results. We can also examine the feedback of the thermodynamics that we introduced, and also just the ambient magnetic field in the corona. So this these runs I thought was really interesting. is we put uniform heating everywhere in the corona. So the same thermodynamics at every single spot. But because the solar magnetic field is so complex, the interplay between the two leads to very different structures that we observe. So where the magnetic field is open, you get less material. Where the magnetic field is closed, you get hotter material and denser material. And then this is just a comparison, again, with one of the best runs to show that many of the features can actually just be reproduced with sort of the fundamental thermodynamics that govern the corona. Also, to better validate this sort of model, we can do quantitative comparisons to observations. So actually, quantitatively take the data that has been observed and then compare it to our synthetic results. And this blue line here, it's probably hard to see, unfortunately, is the new model, and then this green line is what we started with. And you can tweak that model to fit maybe one filter of observations. But to get the thermodynamic structure of the corona right, you really need all these new considerations to be able to fit it at multiple different wavelengths, at multiple different temperatures. So that was an important step in validating this. And just another cool visualization. This is 3D data here from one of the models showing closed field lines. And and it's colored by temperature. So wherever you have the closed field, you get the hotter emission. And this is X-ray emission here. So more X-ray emission, the higher the temperature. And also you can look at how adding these thermodynamics changes the magnetic field. Over here on the left is an extrapolation of magnetic field. In the middle is the original model that we had. And on the right is from one of our thermodynamic runs. And it actually looks qualitatively very much different. And we argued that as a motivation for the thermodynamics being very, very important for dictating the structure. And streamer refers to the closed field lines in the corona. So we have this model, this 18 months of model development is all well and good. So we can synthesize observations, simulate realistic conditions. But now, really, we get to the fun part, which is making EUV waves and trying to study them. So, in other words, blowing stuff up. And again, just as a recap, here's a picture of an EUV wave, and this is the one first one we chose to simulate that was observed in 2008. And again, one of the most important details was this thermodynamic structure. It looks different depending on what wavelength you look at it in. And so we came up with some questions that we wanted to answer with this study. So this is like a laboratory, and in our laboratory we can change various things. So if people think it's a fast magnetosonic wave, a sound wave, well, we can vary the magnetic field. We can vary the sound speed in the corona. And we can say, well, is our simulated EUV wave proportional to this? That goes a long way for determining if it's this theory or not. If it's a reconnection front, can we first see reconnection, one, in our model when we simulate this EUV wave? And can we use that to explain the heating and cooling properties of this EUV wave and things? Also, we can vary how we initiate the coronal mass ejection in our simulation. And we can examine, well, does the EUV wave change significantly depending on how this eruption is initiated? And so that can get us, give some hints as to the nature or dependence of EUV waves on the nature of the eruption. And so this is another picture of comparing models. This is a model synthesis on the top, and third row here, two observations here and here. And the main idea is that, well, we can get close enough to having a realistic picture of these conditions for these observations that we want to compare to. So that's the first step. And then the second part is actually modeling this coronal mass ejection itself. So in this sort of ridiculous picture here is just a picture of the active region. The blue magnetic field is positive, the white is negative. And by moving the base of the magnetic field in the boundary of our simulation, we can cause a coronal mass ejection to happen. And I didn't want to reinvent the wheel for this project, so I used initiation mechanisms that have been developed and studied by my boss, Ilya Rusev, and things like that. So just to recap, as an experiment, we can we can do 4 different runs and vary some key parameters. Sort of the first run is, well, establishing a baseline. So does this look like an EUV wave, yes or no? And then the second run is tweaking parameters to sort of get at the nature of these. So changing the magnetic field strength, changing the eruption mechanism, and also changing, and then also changing the strength of the eruption itself, keeping everything else constant. And then this is just a picture of the 3D data showing how the magnetic field and density change. This color change here is showing a density enhancement, while these field lines here are showing the response of the ambient field in the corona to this ejection. And so you can see it has a pretty big effect. And because it's a computer simulation, we can go in and look at every point in space and examine what's going on here. And then this is a picture showing synthetic observations where we get the same sort of basic properties as in the observations, where at the cooler temperatures, the wave is dark, as in it's heating up, so we're no longer seeing it in the cooler temperatures. And then the higher temperatures, it's enhanced. And so this was trying to demonstrate that we can capture the basic properties of EUV waves in our model. And then here's just another fun movie of the 4 different runs that we did. And they probably all look just about the same, and that's because they're all doing the same fundamental thing. But focusing in on the key differences is really what can help get at the nature of this. So our baseline run here, it's sort of slow. We can see sort of it moves. We see an EUV wave type thing, but it moves much slower than the one where we change the ambient magnetic field, and it actually looks much different when you compare the two. And so, and now taking this a step further, trying to make it more quantitative, you can look at what's called a time distance diagram. So take a position along the sun, and then extract how the flux changes as a function of time. So imagine unwrapping this arc and putting it here, and then watching the emission change as a function of time. And with this sort of plot, this directly tells you both the speed and also sort of first we see an enhancement, and then we see a negative part again. And then this is that same diagram for the various simulations that we did. And I think one of the most key parts to focus in here is there's this big thing here that we call the EUV wave front. But then when we double the sound speed, we actually resolve 2 different parts. One traveling at the fast magnetosonic sound speed, and then another part that's roughly in the same position as the part in our baseline simulation. So this sort of tells us, well, it's not just one or the other. This coronal mass ejection is doing something more than just spewing a sound speed out tangentially across the solar surface, but there's more to the story. And so that was an interesting conclusion. And you can make plots of it just to show how it changes in different temperatures. I won't go too much into that. But essentially, so with these sorts of experiments, you can answer some of these questions, at least start to answer some of these questions. So is it a fast magnetosonic wave? Well, maybe. Partly, yes, because we do find a component that moves at the fast magnetosonic speed. But the peak of the perturbation actually moves below it. And so what's going on here? That's one question. We can address whether or not it's reconnection going on for this part, for the EUV wave. And no, we don't observe reconnection. In fact, it does not seem to be a large factor outside of where the CME happens itself. So that so we don't need this reconnection release of thermal energy to explain the EUV wave properties. And so, and then in this paper we argued, well, there's 2 components. There's the fast mode wave itself, but then there's also the nonlinear perturbation of the coronal mass ejection itself. So you're spewing, you're releasing magnetic energy and spewing a large amount of material out in space, and that's fundamentally changing and interacting with the ambient field and structures in the corona. And so that was our first application of the study. But then in 2010, we were expecting this, and actually it launched relatively on time, which is surprising. We saw the launch of the Solar Dynamics Observatory, and that's what's pictured here. And this is a new NASA satellite that does a lot of things, and has one telescope pictured here called the Atmospheric Imaging Assembly that instead of just being one telescope that's highly advanced with modern technology, it's actually 4 telescopes that's highly advanced with modern technology. So this is a really new and great observational tool that can help constrain and refine what we do as modelers. And just a fun little tidbit, this new instrument, AIA, compared to other instruments that were released in the past. Stereo was released in 2006, and SOHO was released in 1996. So it essentially has 4 times the resolution of what was launched in 1996. It looks at more temperature ranges, and instead of taking a picture every 10 minutes or every few minutes, it takes a picture every 10 seconds. So imagine only being able to open your eyes every 60 seconds as opposed to being able to look all the time. It's sort of that big a difference in terms of examining the properties of EUV waves. But it's also difficult for people like me trying to fit this data on a desktop computer. Yeah, so what's returned in a single day from SDO is a terabyte of information that I'm interested in. And I can't fit that on my hard drive. But and then, you know, it was only 10 gigabytes. I could sort of deal with that. I could fit that in my computer's memory when I wanted to analyze it. And then, so it's, you know, 3 orders of magnitude more than what was launched 15 years ago, and still 2 orders of magnitude ahead of what was launched just 5 years ago. And I showed this picture before, but this is from SDO. And so this is sort of maybe what we could best possibly get with stereo. But there's a tremendous amount of detail. But SDO can actually zoom in on all this detail and observe it change on the timescales of seconds. And so that's really important for a lot of things not related to EUV waves, but also very important for what I study. And so this is an example of an EUV wave at now many, many different intervals, where you can really see not only the front itself, but also various details. There's a secondary component in here evolve as the event progresses. So that's really exciting. It does make my job a lot harder when the observations are so good, but it also helps drive the science, I think. And because it's taking images every 10 seconds, we can take images in multiple filters and combine them into one. And this is sort of tough to get at first, at least for me it was. But you take 3 different filters. In this case, it's about 1 million degrees, 1.5 million degrees, and 2 million degrees, and combine them into the 3 different color channels of an image. And now you can look at the thermodynamic changes in the EUV wave. So wherever it's red, this is going to be hotter. So as the front starts out, it's actually heating up the material. You get more emission at the higher temperatures. And as the front passes, it cools back down again. And so although this was something that we could simulate with in our previous simulation of stereo data, we can now actually look at it directly with this SDO observation. So that's really exciting. And then here's, we wanted to simulate this event. This had a lot of detail. It's been studied by a number of authors observationally, and so we wanted to model this event. And then this is just another example. These are observations here on the left, and these are different sets of 3-color images here on the right. So the idea is we can compare our model results to the observations directly, and this is how we get a handle on how well our simulation captures the thermodynamics of the corona. And what's important is not only do we want to get an average agreement, but we want to be able to agree with the different structures. So this is where there's closed field right here. These blue and cool spots, these are called coronal holes. And also polarity inversion lines is where the magnetic field goes to 0. So it doesn't look great, but it's pretty hard to do on a computer. So this is one of the things we try and do. And now here is an EUV wave simulation for this event. On the left is observations, and on the right is our simulation. And this was really exciting for us because this thermodynamic property that we can now observe directly with this AIA instrument, we can reproduce at least fairly well on large scales with our computer model. And so that goes a long way for confirming whatever conclusions we get out of it. And here is an analysis with a ton of arrows, but essentially what's important is that we can resolve this hot front here. We can resolve this cooling with these green arrows here. So as the front passes, the material reverts back to its original temperature. But also an interesting thing that's it's harder to see in the observations. I didn't make a great plot for this. But there are these stationary structures that sort of stay right about here. You can see it right here. They don't move too much. So this inner part here corresponds to this inner part here. And so there's this secondary part that other authors have argued corresponds to the coronal mass ejection itself. So they say, well, this front part is a wave, and then this inner part is the coronal mass ejection itself. And with our simulation, we were sort of able to get those properties, at least on a qualitative scale. And actually on a quantitative scale. This is a plot showing this top is how the flux changes as a function of time at this point in space right here, and this is compared to the simulation. So in the cool temperature, again, we see it go down, but then in the higher temperatures, it goes up and then down again. And it's sort of this oscillation that is very indicative of a wave nature and is a sort of a modeling confirmation of the thermodynamic properties that we observe. So that was pretty exciting for us. And one of the things you can do with this 3D model is you know how the fundamental parameters are changing in space. So you can go at every point in your model and say, well, let's take our understanding of the theory and what is this exactly? And what I'm showing here is on this color scale, negative is blue and positive is red of essentially the derivative of the velocity perturbation. And then these lines, which might be, I should have made them brighter, here is sort of the center, the strongest part of the density perturbation. And what you would expect from the theory of a fast mode MHD wave is that their phase should look like this. So you have a negative derivative of the velocity perturbation, a positive density perturbation, and then the wave oscillates behind it, and you get the opposite. And so this goes a long way for saying, well, actually, this is a fast mode MHD wave. So that's exciting. And then here's a picture of how that evolves. So here's the start of the event. And then the CME is going out this way, but it's also launching a wave transverse or tangentially to the eruption out into a large part of the corona. And then another thing that helps go to the wave conformation is this thing here. So instead of showing the velocity perturbation, I'm showing the absolute increase in velocity. So one thing that happens in coronal mass ejections themselves is that you accelerate material at high velocities. And actually, the simulation didn't get a very high velocity, but it got enough of one, where the central part, where you see the most color of the eruption here, that's the actual acceleration of material and ejection of material out into space. But these lines here show the density perturbation that we get in this simulation. And so there's no velocity change here, or effectively none, very little. Although if you look at the derivative, like I said before, you can see some, which really goes to suggest a decoupling of the wave and the coronal mass ejection itself. So that was an interesting result. Computer time?
No, what we're observing in real time?
Right.
We're looking at a model, but how long?
Right. So this is absolute time right here. And I'm showing 48-second intervals. And because the simulation took so long, I could only go out to about 52 minutes. So that's what I'm showing here. But 52 minutes is enough, is about the time scale of an EUV wave. So that's what we're interested in studying. This part we may not have done very well, but this part I think is good. And then this is just with some arrows pointing to that thing, where we see that the velocity enhancement of the CME itself is decoupled from the wave enhancement. And so that's interesting. And also, another aspect of EUV waves that I mentioned we see in observations before is its 3D nature. And so we can actually, with this a simulation like this, we can look at the 3D structure of the density perturbation. So here I'm plotting surfaces of constant density change. So, and these are actually very small changes. This outer blue surface is a change by only 0.1%. But we can see that the wave expands uniformly in space, at least initially. And so that gives credence to the wave approximation. But then, as it continues to evolve, it's encountering regions of different wave speeds. And that actually will distort this surface here. And so that's what we're seeing. So at 30 minutes, it's sort of like a spherical shell. But then, as it encounters a high-speed region here, it's starting to be distorted and move out in a very large volume of space. And here's a fun little movie of that. I think it'll work. Yeah, so this is the 50 minutes that I simulated, sort of showing the three-dimensional nature of the EUV wave. And this is one of the reasons it's so hard to interpret the observations, is because all we have is like a looking through the fog 2D slice of these. But with a simulation, you can actually look at them in 3D. And then here's another example. This is the density perturbation here. And then these high color pink regions are high-speed regions, and the blue regions are low-speed regions. And you can actually observe some reflection or reduction of enhancement of the enhancement at high-speed regions, because you're sort of stretching out the wavefront as it passes. And so this is something people had predicted and sort of argued in observations, but it was sort of hard to see before the launch of SDO. And so it's nice that we can reproduce this sort of thing with a simulation. And that's just a summary of the movie I just showed here, where at the slowest parts you get the highest enhancement, because the successive wavefronts can pile up when they're moving slower than being stretched out when they go over high-speed regions with high magnetic field. And then here's another preliminary simulation we did of this other event that happened in August. These are observations here from 3 different spacecraft, and it's exciting because we can see the 3D nature this way, and then also simulate the perspective from the 3 different spacecraft, and that can help you get a handle on it. And I haven't done a full analysis of this, but you can sort of correlate what you see in the density perturbation to what you see in the EUV. And it really tells you that these observations are very, very complex. So as a wrap-up, that was sort of a lot of pictures gone through really, really fast. But the whole idea of this, especially these new simulations of the SDO stuff, is that we can directly simulate the extent of the EUV waves and also their temperature changes. And you can explain this well with a fast mode wave, because that's what we resolve in our simulations. So we get a fast mode wave, and it reproduces the basic observations of what we observe. So that's exciting. But then there's also that second component, sort of what we had gotten at with our first study, that the coronal mass ejection itself will also drive an EUV perturbation that can complicate the signal. And so depending on how that happens, how fast it is, how large an extent it is, you can't always tell the two apart. And that's probably one of the reasons it's been so difficult to figure out what's going on here. And again, the 3D nature is very, very important. Right. And so as an overall summary of sort of what my thesis project has been, I would say that the solar atmosphere, particularly the solar corona, is inherently complex and fundamentally three-dimensional, and that's because of the influence of the solar magnetic field. And I would argue that this definitely needs to be taken into account when you're studying these sorts of things, EUV waves, coronal mass ejection, solar flares, because this has a very tangible effect on the outcome. And also that the 3D magnetic field and also the thermodynamics of the solar corona are very tightly coupled. And so models and observations must necessarily go hand in hand. And I'll finish up there. Thanks for your patience. And if you want more information, please check out any of these websites. Our computational group here at Hawaii has a nice website with a lot of materials. And if you want pictures from this new satellite, you can check out this website. It's really, really great. It's sort of like Google Maps for coronal images. And then also just Googling NASA Sun or NASA heliophysics will get you to this website where they have a ton of information about satellite missions and other things like that. And so again, thanks to all the people I work with, Jeff, and then the University of Michigan team, my thesis committee, University of Michigan, everyone here, and also the people working with the MHPCC. So, thank you. And yeah, any questions?
Yeah, in terms of agreement between the model and observations, I noticed that by adjusting the parameters in the model, you could actually see 2 different speeds and sees speeds of sound in this in one area, and you can see that that's across the field, across the line of sight. And I wondered if the artifacts that you saw in the model with regards to those two speeds of sound observed in the model have been observed actually.
Right, and that was actually the first question I got when I presented this at a meeting. So that's a very good question, and not really. And that might actually change with some of the new observations we're getting with this new satellite, because not all of them have been fully analyzed. But with the data we had before, essentially the EUV wave is so diffuse that it's very difficult to distinguish. Although I would say, let's see, what is it here? So the extent of bifurcation that I showed there probably was unrealistic. Doubling the sound speed from what we thought it would be is sort of a gross change in realism with respect to the real corona. But it did serve to illustrate that they could be decoupled. But at the time, there hadn't been really observations of that. I would say that this might actually be an observation of that, though. This is a new one, this SDO observation, and where you have sort of your coronal mass ejection front here. It's hard to see, but this white part, and then this white part right here, I would say corresponds to this part here. And so you have your sound wave here, and then your sort of the coronal mass ejection part here.
Has this additional satellite imagery from the modern satellites, has this allowed you to adjust the parameters more accurately in your model? Allow more realistic correlation between observation and modeling?
Yeah, so it is somewhat worrisome that not all the satellites agree. One of the problems in space is that detectors degrade, and calibrations aren't always the same. And so we did sort of notice that, actually, that for comparing to this, I had to reduce the heating a little bit. And another thing that changes is the sun is constantly changing. So there's the solar cycle. At solar minimum, the corona actually looks a lot different than at solar maximum. So there's no one model fits all for the thermodynamics of the corona. And we're still at a very rudimentary stage. As probably has been covered in other talks here, the coronal heating problem is still, it's not solved. It's an open debate. And so what we do here is sort of have an empirical approximation that gets the best results for what we're trying to study, the best comparison. But it's by no means constraining that very well. It's sort of the best match that we can make.
Where are we now in the solar cycle that you mentioned?
Right, so we're actually ramping up to a solar maximum. More and more sunspots are going to be coming out over the next few years. And we actually had our strongest solar flare in 5 or 6 years just recently, in February. So we're ramping up. So it's an 11-year cycle, and it builds up to a peak and then slows down to sort of a minimum. And so this is sort of in between. We had an extended minimum, but we're coming up to solar max now.
Is that ramping up good for your research, your observations?
You know, actually, for this particular thing, I don't quite think so. So I'm sort of lucky to be getting out at the right time. Stereo observations were during solar minimum, and so if there was a CME, it was from a very isolated place, and you could see very well the propagation of this thing. But when you have multiple active regions, let's see, I can actually show it here. So when you have something like this, if you get a wave launched here, it's going to hit here and bounce around and things like that. And this is sort of ramp up. When we have full solar max, we can get even more active regions, and that really complicates the signal a lot. So, yeah.
Does CME occur more in certain latitudes of the sun?
Yeah, well, it's you may have heard during the solar cycle we see sunspots appear at different latitudes. So as the solar cycle progresses, the start of the cycle they'll start appearing here, and then over the years they'll start moving towards the equator until the repeat of the solar cycle. And because their coronal mass ejections are magnetic in origin, they follow the sunspot pattern. And the sunspot pattern is what's called a butterfly diagram. If you plot it on a graph, it looks like a butterfly. And so the coronal mass ejection sources will follow the same latitude as sunspots.
Is that due to the differential rotation of different parts of the sun?
No. Well, differential rotation is one of the key drivers for making a coronal mass ejection happen. But I would say the latitudinal effect of sunspot migration, that's due to the solar dynamo, which is related to, the initiation of the dynamo is related to differential rotation, but it's not what we observe at the surface. It's more related to how the magnetic field is recycled and processed over the solar cycle.
Is there any gravitational pull on the coronal mass ejections on the sun at all, or does that not exist?
Well, it absolutely exists. The surface gravity of the sun, just like how the gravity on Earth sets the air pressure here, the surface gravity on the sun will set, or the pressure scale height here, it'll set sort of how the thermodynamic, how the density changes as a function of height in the corona. As far as coronal mass ejections are occurred, they're moving at speeds much faster. They're moving fast enough that they can escape the sun without gravitational effects. But absolutely, in the simulation code, gravitational force has to be included. All right. Well, again, thanks for showing up and sitting through all this. I appreciate it.